In this video we're going to look at graphical representations of inequalities. Starting with the function on the left hand side, I've got a quadratic function which is given by f of x is x squared minus 10x plus 29. What I've shaded is the region where the y values are greater than the function. So everything in the shaded region has a y value which is greater than that of the function evaluated at its x point. So for instance, if we take the point here, the y value 10 is greater than the function which is evaluated for that same x point 4, because the function here is only 5. So everything that sits above this function satisfies my inequality, so that would be the region that we would shade to indicate. Now here my inequality is strict, and because the inequality is strict it means that the line isn't solid, but the boundary is going to be a dotted line. On the right hand side I've got a linear function, this time 7 minus 2x, so again it's sketched out. I'm interested this time in the y values that are less than or equal to the value of the function. Less than or equal to, so now we're talking about a non-strict inequality, so this time I get a solid line. And I want all of those y values that are less than the function. So again, if we pick a value for x, so let's pick 1, this y value is less than the value of the function evaluated at that point. And that's true of everything in the shaded region. What we're going to look at now is how these can be sketched onto graphs. So I've got two separate examples to show you in a program called Geogebra. If Geogebra is not something that you have used before, it's a free application, it's absolutely fantastic, and I would recommend getting involved. So let's look at what happens when we plot these three functions. The first one is going to be 2x plus 5 and all of the y values that are less than that function. So if we plot that onto our graph, we have something that looks like this. Again, we've got a solid line here because we're talking about a non-strict inequality, and all of the y values that are less than the value of that function, so everything that is below my graph. The second inequality that I wanted to sketch was all of the x values that are less than the value of 8. And again, here is a strict inequality, so this time we're talking about a dotted line, and all of the x values that are less than 8 will be on the left-hand side. Finally, I want all of the y values that are greater than -2. Again, it's a strict inequality, so that becomes a dotted line, and the region that I'm interested in, where inequalities A, B and C are all satisfied at the same time, is this triangular region in the middle, where all three inequalities have been satisfied. So outside of that, only some of the inequalities are satisfied. So in this case, only A and C, in this case, only B and C, in this case, only inequality B, and in this case, only inequality A. It is only in that central section where all of the inequalities have been satisfied. For the second example, we're going to look at a quadratic and a linear inequality. So back into Geogebra, what do we have? Well, when I plot out the quadratic inequality, I was looking for y values that were greater than the value of the function, so everything that was above. And if I plot out the linear inequality, then I'm looking for the following. Now, what might be helpful for us to note is that we can rearrange this to make it easier for sketching. What I mean by that is if we take the function and rearrange it so that we've got 3y is less than 12 minus x, and then divide through by 3, we've got y is less than 4 minus 1/3 of x. When I see the function put together like this, it's so much easier to see that the intercept is going to be 4 and that the gradient is going to be -3. So every time I'm moving across one in my x direction, I move a -1/3 in my y direction. So again, what does that mean for my graph? Well, I want the region where both of these inequalities have been satisfied. Well, the region where both of those inequalities are satisfied are the x values that are exactly between these 2 points of intersection. At that point, the inequality will be satisfied because it will be both less than the linear function and greater than the quadratic function. So let's move on now and have a look at how we might represent that. Well, in this case, I've got two separate functions, my green function, which is quadratic, and I've got my orange function, which is linear. Let's say, for instance, to start with, I'm interested in f of x being greater than g of x. Well, for that to be the case, I need the green function to be above the orange function. So that's going to be all of the points here and all of the points here. When do they occur? Well, they occur when the x values are strictly less than 3 and when the x values are strictly greater than 6. So to write my solution set, I would need to say x has to be strictly less than 3 or x has to be strictly greater than 6. If we'd have wanted that the other way round, instead of looking for f of x being greater than g of x, if we wanted f of x to be less than g of x, what we'd be looking for then is a region where the green function sits entirely below the orange function. So this section of our graph here. Now I'm not left with two inequalities, I'm left with a single inequality, because I want x values that are strictly less than 6 and strictly greater than 3. All of these values will give me the green function being less than the orange function. Finally, let's have a look at this question. We've been given two functions here, a linear function and a quadratic function. So the linear function is drawn out in blue, the quadratic function in orange, and we want to look for the points of intersection so that we can find the solutions to this inequality. So from what we've just seen, this inequality, where 2x plus 15 is greater than the x squared graph, we want the points where the blue graph sits entirely above the orange graph. So we want all of the x coordinates that refer to this region of the line, because for all x points on this region, the blue line sits entirely above the orange line. So how to do that? Well, first of all, we want to find these points of intersection. So we want to find out the points where x squared is equal to 2x plus 15. Now to do that, we rearrange x squared minus 2x minus 15 equals 0, and I'm going to factorize that into x minus 5 and x plus 3. So that's going to tell me that x is either equal to 5 or x is equal to negative 3. Now I wanted to find the points of intersection, so let's do that for completeness. Let's find the associated y values. Well, that's dead straightforward, because the associated y values are just going to be the square of the x value. So here it would be 25, and here the associated y value would be 9. However, I really only need to give the x set of solutions for this. So the point here was negative 3, the point here was positive 5. We only wanted the region in between those 2 points. It's a strict inequality, so I finish by saying that x must strictly sit between negative 3 and 5.